Dirac operator. dA, which maps fermentation interval. And then flow a little bit. Let's think about it a tiny bit more. In fact, just for a moment, think about it on R4. So, if just for the spin guide for simplicity, just to get a little bit of a feeling of what this guy looks like. So, actually, I want to look at the R3. R3, it's the Kählerian notation. This is what it looks like. Acting here, the quaternions are acting on H. This is that. The interesting thing, one interesting thing to notice about this guy, so again, just this is self-adjoint because when I take the adjoint of differentiation, it can be minus differentiation, but each of these pairs is the skew adjoint matrix. And so self-adjoint, and if I look at its square, then what happens? Well, if I just square each of the terms individually, we're going to get Laplacian. Right? But then there's some cross terms, and one of the cross terms are things like this, but quaternion multiplication is anti-commutative, so the cross term vanishes. Vanishes all of them. So this operator is the geometers of Laplacian with a minus sign as positive spectrum times the advantage. This has an important generalization to an arbitrary manifold, which is Mrowitz's formula. And it says the following. So if I look at the square of the Dirac operator, first spin case. The square of the Dirac operator is what's called a rough Laplacian or covariant Laplacian. Generalizing this term, and then plus 1/4 the scalar curvature. So this is now for the spin C case. It's a little more complicated. I'm not going to prove these things. It takes some a bit serious computations, but In the spin C case, right, the Dirac operator depends on this connection in the determinant line bundle. And what does this term mean? Well, the curvature is a section of imaginary two forms, curvature of a connection in the line bundle, Hermitian connection in the line, imaginary line bundle is a imaginary two form. Now, Clifford multiplication gives us a way of acting on spin. So what I mean here is that I think of, again, the Clifford algebra is isomorphic as a vector space to the exterior algebra, so I use that isomorphism to think of this as an element of the Clifford algebra, and then I can Clifford multiply. Okay, so that's what the formula in the spin C case is. Now, Lichneritz's formula has an interesting consequence. So remember, we figured out what the index was in dimension 4. The index of the Dirac operator is minus an eighth the signature, and in C case, minus an eighth the signature, minus the signature plus C1 squared over 8. So these formulas tell you something interesting about the kernel of the Dirac operator. So you notice that if p phi equals 0, then b squared phi equals 0. So that's the covariant Laplacian plus the scalar curvature of the form times b. And now what I can do is I can take this pointwise equality, I can take the inner product of phi and integrate it over the manifold, and then so the inner product of phi b squared L2 inner product, that's going to be equal to the covariant velocity, the inner product, inner product on the other side. And now, the Dirac operator is self-adjoint. This is the adjoint of this guy. So this formula implies this formula. Right. And this, if we're assuming that this is 0, we learn that this is 0. And if the scalar curvature is positive, or non-negative and positive somewhere, this implies, this is 0, but both of these terms are non-negative. So it implies that phi is, covariant derivative of phi is 0. That means it's parallel. And if r is non-negative somewhere, it also implies that phi is identically 0. So it's at least parallel. If it's greater or equal to 0, it's at least parallel. If it's non-zero somewhere, then it's identically 0. So this implies that the index is 0. Right. And so that was an important and surprising result. When Kähler proved it, he proved it, and that's gone to an important theme in understanding the relationship between geometry and topology. This is telling me that the A hat genus, which is the index of the Dirac operator in general, is 0 on enough of a positive scalar curvature. So now, in dimension, going back to dimension 4, I'm thinking about this story. I should clarify this a tiny bit. This is sort of general case, but in dimension 4, I decided I should, let's put that, okay. So remember the spin C case I was talking about, in dimension 4, is the covariance, this dA and dA star off diagonal. The point I want to make is that there's something interesting about how Clifford multiplication acts. So, remember, so Clifford multiplication, that's the Clifford algebra of the cotangent bundle isomorphic to the exterior algebra as a vector space.
Wait, what's the preferred vector space isomorphism?
Sorry, what?
What is that preferred vector space isomorphism?
What is the isomorphism? So the isomorphism is by taking the associated gradient. So this is a filtered algebra. This is associated gradient, but that the map is an isomorph. You know, the map from a filtered vector space to its associated gradient is a vector space isomorphism. It's a vector space over C. There's no funny business going on in the filtration, no reporting stuff. But you know, or just more concretely, C of E1 wedge E2 is C of E1 times C of E2 if E1 and E2 are perpendicular. And you notice if they're perpendicular, the Clifford relation tells you that if I switch these guys, it changes sign, and obviously if I switch these guys, it changes sign, so that makes sense. So that's concretely gives you a map from the exterior algebra to the Clifford algebra. Okay, so yeah, okay. Now, so I have this formula. And if I look at star, if I look at dA squared, and going back to dimension 4, dA squared is still the covariant Laplacian. So this is a formula. This is for phi. Let's write it this way. Applying this to phi section of S plus. This part, there's no confusion. So I have Clifford multiplication by the curvature in the sense applied to phi, but something interesting happened. Phi is now a positive spinner. The curvature is a two-form, but not all of it actually does something. And what in fact is happening here is that only the self-flow part of the curvature of the connection is acting non-trivially. If I looked at the adjoint, that's the part that acts on S minus, I would find F minus here. Okay, so in dimension 4, there's this interesting, again, special story that happens only in dimension 4. This formula is true in any dimension, but there's no decomposition of curvature analogous to that. Here, this is dimension 4. Okay, now, all right. But we have this interesting vanishing theorem for the spin Dirac operator. And you might hope that somehow there's an interesting vanishing theorem for the spin C Dirac operator. So obviously, in some sense, this is some endomorphism of the spin bundle, and if the endomorphism has a sign. But by the way, I should say, so C, you know, two forms to skew Hermitian in those. But that means that IS plus maps to Hermitian endomorphisms. I'm going to say I, and they're actually traces, so ISU of S plus. So the point of saying that is that that's a Hermitian endomorphism. It has real spectrum. So you could ask yourself, is the spectrum of that endomorphism pointwise positive? In which case you'd get a vanishing theorem. But okay, now there's a little more magic that happens. So in fact, this Clifford multiplication, there's a map like that, but in fact, it factors through the projection to lambda plus, and this map is an isomorphism. Okay, this is three-dimensional. This is a two-dimensional vector space, so the Hermitian endomorphisms are a three-dimensional vector space, and this map is an isomorphism between those two three-dimensional vector spaces. Okay. If I have phi in S plus, this section of S plus, I can construct another Hermitian endomorphism of S plus. In fact, traceless skew Hermitian endomorphism. What I can do is look at the, well, I can think of phi tensor phi star as an endomorphism of S plus. It's the endomorphism that takes the inner product with phi and then multiplies that with phi. Right, so that's I u of S plus. C to phi. That's nice. Poetic notation for it. But it's not traceless, so let's take the traceless part. The trace of this guy is just the length of phi squared, and it's in a two-dimensional vector bundle, so half phi squared with the identity. Its trace is the length of phi squared. The trace of this guy is phi squared. So this is traceless. So from the spinner, I got a traceless Hermitian endomorphism, but that's the same thing as this imaginary self-dual form. So I'm going to define in this way a map which is called sigma for today. Yes. So define sigma so it's a bundle map but nonlinear. Sigma of phi is characterized by the property that C of sigma phi is this guy. Okay? So that's the kind of algebraic way to write it. Let's demystify it a tiny bit. This is That's a map from R4 to R3. But you notice it's a quadratic map, it's not a linear map. Right? And what this map is, sigma is the cone on the Hopf map. From S3 to S2. So this is sort of an algebraic way of writing down an instance of the Hopf map, the standard interesting map from S3 to S2. And this is kind of the cone on that map. And one interesting consequence of this is that the only thing that gets sent to the origin by sigma is the origin. Yeah.
Can you say again what is this R4 and R3?
So sorry, the R4 is what this is a four-dimensional as a real vector. You know, the fiber. This is a bundle map from a C2 bundle, but I'm thinking of it as a real rank 4 bundle, to a real rank 3 bundle. So I'm saying fiber-wise, what it looks like is the cone on the Hopf map. Okay, does that make sense? I mean, for later purposes, I could have said this, but it's important to understand this formula because it'll play well with a bunch of other formulas. So, all right. So that's the key player. What does that let you do? Well, we already we've got the Dirac operator. Well, now we can do something interesting. We also have our connection. We can take the self-dual part of its curvature. That's an interesting pair of equations for this data, but it's the A is only coupling back to phi in the Dirac equation, but using this guy, I can make it even a bit more nonlinear. And that's what I'm going to do. I'm going to stick in sigma phi here. Right? That makes sense because it takes a positive spinner and gives me an imaginary self-dual 2 form where the curvature, self-dual part of the curvature of the connection lives. And this is, well, if this was the Dirac operator, I'm going to call this the Seiberg-Witten operator. So that's going to be the main character in the story. We want to understand this Seiberg-Witten operator and what it tells us about life. There are a couple of that's the Seiberg-Witten operator, and actually I'm going to give it a name and some notation. So I'm going to call it SW, and what does it do? It takes that's connections in the determinant line, tensor sections of S plus, and then it gives me, I'm going to write them in the other order, I think. Sorry, not tensor, just times. And the output is it is going to be a section of self-dual forms, imaginary self-dual forms, and a negative spinner, and SW phi is just this thing. So then there's the Seiberg-Witten equations. That's the solutions to this equation. Both of those, so phi is supposed to be a harmonic spinor with respect to dA, and then this interesting self-reported curvature is supposed to be sigma of phi. So okay, and
Sorry.
yeah, sure.
Now you switched around, right?
Yeah, I switched them around.
So dA
Oh, sorry. Yeah,
is
right.
something special.
Yeah, I tried to switch them around. Okay. Yeah, sure.
Can you say what that sigma was?
Sigma is this map. So it's defined implicitly, right? Sigma is
It's
defined.
by the equation also.
Yeah, that's right. So sigma of phi is the thing that when you Clifford multiply by it, it gives you that traceless part of the projector. Yeah. Yeah. And that's the way we're always going to use the formula. So it sort of just, I don't want to give notation for the inverse of Clifford multiplication. I mean, I could also put inverse of Clifford multiplication. Anyway, so this is the Seiberg-Witten equation. It turns out to be we'll also study this equation where A is some fixed imaginary self-built form. But, that's the perturbed Seiberg-Witten equation. Now you'll see in a moment why we don't do anything here, but just here. Okay. So, by the way, just as a so this is some kind. These are solutions, or in the original Seiberg and Witten papers and Witten's paper, that these are called monopole equations. The point being that this is very similar to, in some sense, to the equations, like I was saying before, that you would think of that govern, if you look at the Lorentzian version of this, that govern an electron in a electric field. So the connection A is the electric magnetic field, in 4 dimensions. So A is like the electric and magnetic field, and phi is, well, the electron. And so this is, in some sense, you're supposed to think that's how they're interacting. All right. So these are the equations. We want to understand solutions to them. And so I want to point out that maybe first observation is symmetries. So there's symmetry. So if I have a I'd like to see if there's any kind of transformations of A and phi that leave the solutions invariant. And it turns out that the symmetries are, because this comes from physics, it's called the gauge group. It's so G, but it just maps from X to U1. And if I have such a map, how does it act on this stuff? Well, so the kind of initial way that you're thinking about this is that it's, you should think of this as action of scalar multiplication on the spinner. So u dot phi is u phi. Just it's a map to u1. Spinner is in a complex vector space. It makes sense to do that. That's what I'm going to do. Now, I need to be a little bit careful. I want the Dirac equation to be preserved, and I need to have a way of acting on connections to do that. And the only tricky thing is that, this u then maps sections of S plus to sections of S plus, and it induces then a map on the determinant bundle on sections of the determinant bundle. But remember, the determinant bundle, I didn't say this, but the determinant bundle in terms of S plus is, it's the complex determinant line of this two-dimensional vector bundle. So two-dimensional vector bundle, I can look at wedge 2 of it. That's what L is. LS is lambda 2 of S plus, which happens to be also lambda 2 of S minus. But if I'm multiplying here by u, then u on a section of L, its action is equal to u squared times lambda. This being complex multiplication, this is the action induced from this action. Okay, so does that make sense? This one comes from here, but this is just scalar multiplication. Okay, so but my A was a connection in L, right? So this is telling me, so I know how scalar multiplication is supposed to transform connections. Right? So for a connection in L, if I have V, the induced action, naively you'd think that what you should do is, remember, connections is an affine space, and naively what you think you should do, you think this should be the action. If you were acting by just scalar multiplication by u, that would be right. That's not quite right. It's u squared because it's actually acting by the square of scalar multiplication by the square. But now I can work this out a little bit, just to have the right formula. This is minus 2u inverse du. Oh well, we have to carry on that factor if you want to get it right. That's okay. But the important thing is that now, with this action, the action on the covariant derivative of phi is equal to the action of the u on the connection and u on the spinner. Okay, and that implies that the Dirac u of the Dirac operator is the Dirac operator applied to the transform of the connection and the spinner. So that's cool. And now, what about sigma? So, yeah, by the way, you notice that FA of U phi is a because I'm going to take D of this guy, and that's 0. So the action on curvature is to fix it, curvature of the connection. But if I take sigma of U phi, well, that's U tensor U. That's U phi tensor U phi star minus now half the length of U squared. That doesn't change. But this is U phi tensor U bar phi star. And that's sigma of U. So that's perfect. Then we check the Dirac operator. When I act by U on both of these guys, the Dirac operator gets multiplied by U. And when I act on when I look at the curvature part of the equation, F plus of A is invariant of a gauge transformation, and so is sigma. Right. So the upshot is that the upshot is that for the action U on acts trivially on sections of lambda plus, and then U acts by scalar multiplication on sections plus minus S W of U dot A. Phi is equal to U SW A phi. So it's an equivariant map, and that explains why this equation is a sensible equation, because there's no action on the first coordinate. But if I acted on the second coordinate, then the solution set wouldn't be invariant. Okay, so, all right. So that's the Seiberg-Witten map, and so the kind of now, notice so why did we pick this particular nonlinearity? I mean, it seemed like a reasonable thing. Maybe why did I put a minus sign in front of sigma instead of a plus sign? But sensible question, right? In fact, there are people in the universe who put a plus sign there before Seiberg-Witten put a minus sign. And they were not dumb people. Wasn't me. But anyway, okay. Now let's. What?
What happened?
They got upset.
I got upset after Witten's paper came out. That's for sure. Okay, why is that an interesting thing to do? Okay, so let's, well,
Maybe just, I mean, where did this develop from? Why are you looking at maps from X to 1? I mean,
well,
like this G, did you get
yeah, why? Well, it's certainly a reasonable thing to try to do to phi. Right? What's the thing that acts on phi in a natural way? Well, it's sections of a complex vector bundle. The only thing there is scalar automorphisms. Right? That's the only kind of invariant thing unless the bundle has extra structure.
I mean,
So,
could you have replaced it by somehow sections of some U1 bundle over X, and then you fiberblind it?
well, I mean, yeah, I could have acted by endomorphisms of S plus. That's true, but we're not going to do that. Let's do the simplest possible thing. I mean, we didn't want to have the Dirac equation preserved. And I think if you think about it for a bit, I mean, there's no the only thing that's acting on connections is this union thing. So there's no way to get endomorphisms to really act. Anyway, okay, so right, what? In the interest of time, I'm not going to beat around the bush. I'm going to get to the key thing, and then we will, in the proof, you'll see where the magic happens. But okay. All right, so what we're going to do is show that if I take SW of AD, take the L2 norm, so that just, I don't want to write it out more explicitly, but I'm just taking the L2 norm of this guy and the L2 norm of that guy, and adding them together. Right, that's all that means. Then it has a remarkable expression. So it plus 1/8 the scalar curvature squared Duval minus 2 pi squared C1 squared LS evaluated on X is equal to the L2 norm of phi squared, equating to phi squared, plus 1/2 the L2 norm squared of the curvature, and then plus a slightly strange looking term, but it is what it is. Okay, so some of this you kind of is perhaps not surprising. Right? When I take the L2 norm squared, in particular, I get the L2 norm squared of the Dirac operator, and from the Weizenbach or the Kähler formula from before, that is giving rise to a term like this. There's a scalar curvature. So if I look at the cross term in here, what is it? Well, it's 1/4 the scalar curvature times phi squared, which is also what happened in the Weizenbach formula. But then there's other stuff. But what do you notice about this? This is non-negative, and this is non-negative, and then there's this stuff. Right? So you're starting to, that particular choice started to give you some signs that are like the signs that happened in the positive scalar curvature case. But now, and that wouldn't have happened with the wrong sign.
Can you say why it's the energy identity?
So energy is because the bottom looks like energy. I mean, remember, what is energy to a physicist for real? No. It's whatever they want it to be. Except that it shouldn't look like an energy. And that's, energy doesn't have, energy relative to what? It's what you need to be in a problem. And that's the first term. Well, it's a gradient or something. That's like a kinetic energy. The second term, well, it's the derivative of the one form. That's also like a kinetic energy. And then there's some potential term. So it's that. That's the energy. So let me kind of try and sketch the proof of this. Which is a brave thing to do, but we'll do it. Okay, so that's the Weizenbach formula that is going to give me this thing here, and then 1/2 the L2 product of Clifford multiplication by f plus phi, a little bit of algebra shows you that this term, actually, I can replace it with twice. I can think of this rather than as an inner product of spinors. I can use the This is, by the way, that isomorphism between self-rule forms and the morphism of the spin bundle. That's not an isometry. There's a factor in it, and the factor is going to come in here. But I can think of throwing this guy to the other side, thinking of this as an inner product in endomorphisms, and then there's a factor of 4 between those guys, and then this thing becomes sigma phi. When I throw it over to the other side, this guy when I just throw it over to the other side, I get phi tensor phi star, but this guy's traceless, so I get the traceless part for free. Okay, so that's good. And now, if I take, sorry. Then I want to get rid of the C, right? If I put a C here and a C here, it would just be the same thing. But if I get rid of C, there's a factor of 4 between them. That's better. Well, if I expand out this guy, it's plus squared minus 2 plus inner product sigma phi L2, and then sigma phi L2 norm squared. Okay, now I stare at this, and if I stare for a really, really long time, I notice that this term and this term are the same except they have opposite sign. So now I add them up. And on this side I get the L2 norm of Seiberg-Witten math, and then I get let's think about this guy before I write it. So I've just copied the terms. These guys cancel when I add them up. What about this guy? So this guy is fourth order in, when I take the L2 norm, the square of this guy, it's fourth order in phi, and it's just a multiple of the pointwise norm of phi to the fourth. And it turns out to be 1/8 the integral of phi to the fourth. This term is equal to this. So again, similar factors of 2 coming in this. Okay? All right, so that's pretty close to what we have. We've got that term, that's okay. That term, well, that term, this term, and this term, I can complete the square. All right? So if I look at these two terms, I won't do that for you, but that's, that's, when I complete the square, I add 1/8 the square of the integral of the square of the scalar curvature to one side, and then it becomes a perfect square, and that's what it is. The remaining thing is that is this integral of f plus, and where here I have f plus, and there I have f. And there's a half there and there isn't there. What's the explanation for that? Well, the point is that I over 2 pi fa is equal to, it's homotopy class is C1 of LS. It's the curvature of our conventional line bundle. That's what we know. So that tells us that C1 squared of S evaluated at X is equal to minus 1 over 4 pi squared, the integral of FA fudge FA. The only thing that drives you nuts at this moment is the eyes. Okay? So you just have to do this calmly and patiently. And when you keep track of the factors of I, and that's true, but then each of these guys is actually an imaginary form. Let's think of pulling that out, and then where's my formula? Yeah, okay. So each of these guys has a factor of I. Let's think about pulling that out. That gets rid of that sign. And then as far as norms are concerned, this becomes, remember, this is a wedge product, but it relates to the norm it's the L2 norm of the self-dual part minus the L2 norm of the anti-self-dual part. The sun is because of the eyes that were there. Okay? So that's great. All I do now is, on the other hand, L2 norm of S plus is L2 norm of F is L2 norm of F plus L2 norm of F minus. I just now add these types together, solve for F plus, and plug it in, and I get that formula. Okay? So, anyway, you have to do this privately for yourself, otherwise why should you really believe it? But that's just a sketch. So, that's a remarkable thing. What are some corollaries about that? So one corollary. We'll see. then eventually there's a tremendous amount of stuff that just follows from this one equation. Well, you know. So one thing to notice is that if if he solves the Seiberg-Witten equations, then one thing I learned was there's my formula. If it solves the Seiberg-Witten equations, that side 0. Those two, the other two things on the same side as the equations, is they're constants given the spin C structure. So it's telling me that, essentially it's telling me that this guy and curvature rate are L2 bounded uniformly, and phi is L4 bounded. So we're getting already some kind of control over the solutions to the equations, just from staring at that. And another thing that we learned is that, thinking about it the other way around, so if the Seiberg-Witten equation, Seiberg-Witten map is 0, Seiberg-Witten operator is 0, then, well, that stuff's all positive, so that's telling me that the integral of square curvature squared over 4 is greater than or equal to 2 pi squared c1 squared s, evaluated from x. So the important thing is that there's an upper bound for c1 squared for any solution. So that's telling you, independent of the spin c. So this bound here, the bound depends on the spin c structure. On the other hand, this bound doesn't. And it's giving you some kind of control over what C1s can have solutions. Now, next time, we'll learn about the dimension formula for the Seiberg-Witten equations, and the dimension formula for the space of solutions is a positive multiple of this. So this is going to tell us that actually there are only finitely many spin C structures for which there can be a non-trivial solution. And there are easy generalizations to this. If I have a solution to the perturbed equations, then there's just going to be a squared, extracted squared term there. So let's see. Let me just say, well, let me just say one other. So a consequence of this is we're going to. Right now we're controlling the L2 norm of the curvature, and we'd like to control the L2 norm of the connection. Not just, we'd like to control norms of the connection itself, not the curvature of the connection. And it turns out that, well, I'll explain how you do that next time, but essentially, if you add a side condition on the connection, then an L2 bound on its curvature will give you an L2 bound on the gradient of the connection 1 form. And then this stuff, after adding the side condition, is going to tell you that a kind of variant of the Seiberg-Witten map is actually a proper map. So what we're going to get out of this story, after a little tweak, is that not quite this Seiberg-Witten map, but a very close. I'm going to add another equation. That new equation is going to give us a proper map between Hilbert spaces, and we're going to just derive invariance from such a proper map. We're going to, in simplest Guy's sort of old Taylor-Schwartz proper map between Hilbert spaces gives rise to a frame manifold and therefore an element of stable homotopy groups of spheres. And then equivariance, blah, 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 will follow. But, okay, I think it's time.